Hey guys, so let's talk about 8.5. This is going to start with the polar form of complex numbers, and we're going to do some operations on those, like de Moivre's theorem and finding the nth roots. So where we need to start though is to make sure we're all familiar with the form of complex numbers that we're used to, which is called the rectangular form. So a lot of times when we talk about a complex number, we give it a letter. So in ALEKS and in our text, we like to use Z. So we think about Z equals our complex number A plus BI. So this is the form you probably would recognize. Where A and B are both real numbers, I is the imaginary unit. That's what gives this number an imaginary part. So I'm going to change things just a little bit. Instead of using A and B, I'm going to change that to an X and a Y. And I'll show you why in a minute. So if I call it X plus YI, it makes more sense to us when we plot these in a plane. Now, you will have to plot complex numbers today. But because of the imaginary part, because of that I, you can't actually plot them in the normal XY coordinate plane. We use what we call the complex plane. It looks just like the normal plane, but instead of having an X and a Y axis, we usually call this the real axis and the imaginary axis. You can think about real and imaginary as X and Y, and it will help you plot. So let me give you an example of a complex number we could plot. Let's say we have Z equals 8 plus 3I. So when you're plotting, you actually don't do anything with the I. The I being there with the 3 just means that the 3 is what we call the imaginary part of this complex number. The 8 is the real part. In order to plot something, I need coordinates. So you guys, 8 and 3 are the coordinates that I'm going to plot here. That's why I like to write my complex numbers as X plus YI, because you can say, oh, well, this is X, this is Y, and you know how to plot that. So 8, go over 8 on the real axis, go up 3 on the imaginary, and you have your point 8 plus 3I. I could plot one more. Let's say I want to plot Z equals -1 minus 4I. You guys, these two negatives will go along with your X and your Y. So I will go down -1, so -1 on the X axis, or on the real axis, so we went to the left 1, down 4 on the imaginary, and we're here at -1 minus 4i. So you can see how the complex plane really just works the same way as the XY plane. So that's why I like to use X and Y for my complex numbers. Now I'm going to erase the specific points we graphed here so I can talk about a more general form. Because one of your goals today is to take complex numbers and convert them from rectangular form into polar form. So with the R and the theta, like in 8.3. So let's disregard these units, you guys, because what I'm doing is a general. I don't want you to think it's for specific points. Okay, so let's say I've got a point in the plane, and it can be anywhere with any real and imaginary part, any X and Y, and I'm just going to leave it as X plus YI. Obviously the rectangular values here tell us where it is on the rectangular complex plane. But on the polar plane, remember R and theta are the coordinates we're looking at. So you guys, let's talk about R. Remember on the complex plane, or I'm sorry, on the polar plane, it has all these circles. And the circles are what tell you what R is. It's basically exactly the distance from the origin to the point. The circles each had a radius of R, so we went out 1, 2, 3, and on. So you guys, if I'm looking for a distance to find r, I could symbolize it this way, even on the rectangular complex plane. And then remember the other value we used for polar coordinates is theta. Where is theta here? Well, you can see it. It would be right here. It's this angle, just like in the rectangular plane, just like in the polar plane. Theta is always this angle here that is created with this axis here. Okay, so how to find r and theta? Well, if I drop down the right triangle, you guys, this is y value, this is the x value. It looks exactly like it did from 8.3. R and theta are going to be found using the values of x and y, just like I did when I converted normal rectangular coordinates to polar form. So, finding r and theta, do you remember how we did it? Well, we said that r, like it has been all semester, is the square root of x squared plus y squared. Still finding it that way, even in the complex plane. Theta, remember we talked about theta being the inverse tangent of y over x. This still holds true, even though we're in the complex plane. So let me erase some stuff. The problem is, in 8.3, we went from these rectangular coordinates to another set of coordinates. So we went from an ordered pair to an ordered pair, x, y to r theta. Okay, but you guys remember your complex coordinates aren't written like this. They're written in this form, x plus yi. So if we start with x plus yi, we're not going to get a coordinate pair, so finding just r and theta and putting them in a pair is not going to be enough for complex numbers. They need to still have the same template of a real part plus an imaginary part. So r and theta is involved, but it's a little more involved than that. All right, so do you remember, a whole, 2 hours ago, since I made the last video, we found that x can be written as r cosine theta, and y could be written as r sine theta. You guys, these two equations are true for any xy that goes with a coordinating r theta. Complex, real, it doesn't matter. So I'm going to use this fact to help me find the polar form of complex numbers. So it has to stay x plus yi, but instead of x, I'm going to write r cosine theta plus yi, instead of y, I'm going to write r sine theta, and then there is an I in there. And while this is the polar form of the complex number, we clean it up a little bit. We do factor out this common r from both terms. So what we end up with is an r in front. In parentheses, we have cosine theta plus, and we're going to put the I in front of sine theta. So you guys, you start with a complex number in rectangular form. You end with a complex number in polar form. Notice, how can you get polar form? You have to find r and you have to find theta. These two thetas are the same theta. But once you find r and theta, you just put it into this form right here as is. So let's look at an example. Okay, so I want to take the complex number z equals 1 plus I, and I want to convert it to polar form. So we have to be able to recognize the x and the y terms. Remember, it's x plus yi. So obviously x is 1, and even though you don't see it there with the I, you could put a 1 in there. So y is also 1. One thing to remember, never include the I in your X or Y. Remember, the I shows up on its own and it just stays I, so your X and Y are just the number parts. If X is 1 and Y is 1, let's find R. Is the square root of X squared plus Y squared, as always. So square root of 1 squared plus 1 squared, that's the square root of 2. And we'll leave it as the square root of 2. So we found R. Let's find theta. Remember, theta is an inverse tangent of Y over X. So that's the inverse tangent of 1 over 1. And you guys, where is tangent 1? Well, it's tangent is 1 at pi over 4. So you guys, the inverse tangent of 1, I'm a little crazy on the board right now, but I get a theta of pi over 4. So remember, you don't just write it as r theta, you write it in this form here. So I could say that if your complex number was 1 plus I, in polar form, the r goes in the front, so that's where our square root of 2 is, equals, or not equals, I don't know why I wrote that. Hold on. I'm not going to stop and start over the video. I'm not going to do it. I'm just going to keep going. Power through. All right, so I have r. This is where the theta you just found goes. So theta is pi over 4. So I'm going to write cosine pi over 4 plus I times the sine of pi over 4. So you find r and theta using x and y just like you did in the last section, but you write it in this form here with the r cosine theta plus I sine theta. One thing I want to mention before we move on to another example is when you're in polar form, theta has to be between 0 and 2 pi in radians, or in degrees, it would be between 0 and 360. So notice here, theta needs to be positive within one rotation. So if we ever get an angle that's not positive, we're going to actually have to make it positive to write it in the polar form. So just keep that in mind as we do some more examples. Making a little sketch like we did in 8.3 when we were converting to polar form, making a little sketch of where the point is to help you find your angle is always a good idea. We didn't do it on the last one because both x and y were positive. I knew that was just going to be a simple first quadrant angle. But let's change that one up just a little bit. What if I have z equals -1 minus I? So I know there's a 1 here. I could stick it in and I could know that's my y value. So if I say convert to polar form, first thing you want to do is find r. So r equals the square root of x squared plus y squared. X is -1. Y is also -1 here. -1 squared plus -1 squared is still +1 plus +1. We get the square root of 2 again on this one, but that's not why I want to do this one. You guys, it's when we find theta. Before I find theta, I'm going to make a little sketch of my angle. So you guys, sketch the complex plane. Remember, it's the same as the rectangular, basically. Go -1 on the x-axis, -1 on the y. You guys, our complex number is down here in the third quadrant, so just keep that in mind when we find a value for theta. So theta is the inverse tangent of y over x, so -1 over -1. You guys, we get that same inverse tangent that we got on the last question. We're looking for the inverse tangent of +1 again. You guys, when I did this on the last question, I said, oh, Tangent's 1 up here at pi over 4. And that was my answer because both x and y were up here. They were positive. But could I use pi over 4 now? No, I need the angle in the third quadrant where tangent is positive 1. So you guys, it is going to be a pi over 4, but it's not going to be pi over 4. It's going to be 5 pi over 4, the one in the third quadrant. So theta is 5 pi over 4. So we always want to make sure our angle actually matches the little picture. But r is square root 2, theta is 5 pi over 4. So our complex number in polar form is going to be the square root of 2 times cosine 5 pi over 4 plus I sine 5 pi over 4. And you guys, once you write it in this form, remember there's nothing else you have to do here. You just leave it here. This is the complex number in polar form. All right, so let's do something a little different. Okay. So one thing that's nice about the polar form of complex numbers, because you might be wondering, why would you ever write it in polar form, right? I mean, it looks a lot more complicated. But there are some nice operations that you can do in polar form that are a lot harder in rectangular form. So one thing I want to do is I want to talk about multiplying two complex numbers together. So maybe you have a z1 and a z2, and you want to multiply those together. So let's say z1 and z2 are both complex numbers. Let's say that z1 is labeled as r1 times cosine theta 1 plus I sine theta 1. So just the general form with the little 1 saying this is the first complex number. Let's say z2, let's call that r2 times cosine theta 2 plus I times the sine of theta 2. So we have two separate complex numbers, two separate r's, two separate thetas, but I want to multiply them together. So I want to know, what is z1 times z2? And it's actually really easy to find. So when you want to multiply two complex numbers, the first thing you do is multiply their r's together. So in front, your new r will be r1 and r2 multiplied together. In here, I need to find my new theta. Notice I'm leaving the same form because it's still going to be in complex polar form. But it's not going to be theta 1 times theta 2. So we did multiply the r's, but you don't multiply the thetas. You actually add the thetas. So it'll be theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So your goal is when you multiply them together, you have to find a new r, you have to find a new theta. The new r comes from multiplying r1 and 2. The new theta comes from adding theta 1 and 2. So you always add the angles, you multiply the r's. Let's look at an example. All right, so z1, our first complex number, is 5 times the cosine of 2 pi over 7 plus I sine 2 pi over 7. Your second complex number is 10 times the cosine of 13 pi over 14 plus I times the sine of 13 pi over 14. So what I would do on these is find your new r and find your new theta. Remember, your new complex number is going to be z1 times z2. So your new R is going to be R1 times R2. Remember, you multiply the R's. So it's going to be 5 times 10. And the R you're going to use for your product that you get is 50. So new R is 50. Remember, the template's the same. You just have to find the angle, because all that you're missing now is the new theta. So let's find the new theta. Remember, to find the new theta, you take 1 and 2. You find the two angles already that you have, and you add them together. So our new theta is going to be 2 pi over 7 plus 13 pi over 14. You guys, when you're in radians, you got a lot of fractions. We're going to have to find common denominators to add these two fractions together. But you guys, it'd be pretty easy to get a 14 on the bottom there. So take it up to the side. Remember, you have 2 pi over 7. You want something over 14. Well, to get the bottom, you have to multiply by 2. Just make sure you multiply by 2 on top. So 2 pi times 2 is 4 pi. So you guys, instead of writing 2 pi over 7, we're going to write 4 pi over 14. So I have 4 pi over 14 plus 13 pi over 14. So what I end up with is 17 pi over 14. So you guys, that's your new theta. Oh, I'm writing 13 again. Hold on. So you guys, your new theta is 17 pi over 14, and it goes in both places where theta goes. So you guys, this is Z1 times Z2. So easy. Multiply the R's, add the thetas. So what if I wanted you to divide complex numbers? It actually follows really well, really easily from the multiplying. But let's talk about it, and then we'll do an example. So if you have two complex numbers, Z1 and Z2 again, but this time you don't want to multiply them together, you want to divide. Let's say I want Z1 divided by Z2. Remember, Z1 and Z2, R1, theta 1, R2, theta 2. I'm not going to write that again, but I am going to write how to divide them. So if you want to divide two complex numbers, you divide the R's. So it says divide, you do that to R's. You do R1 divided by R2. What do you think is going to happen with the angles? Do you think I'm going to divide the angles? No, I'm going to subtract the angles. So, like I said, it follows really well. With a product, I added the angles. With division, I subtract. Make sure that theta 1 goes first, and R1 goes on top, because order matters. You're doing 1 over 2. You need to keep it 1 over 2. So in here, I'll have cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. So let's do an example. Let's stick with that same one we were using before. Let's say that Z1 is the 5 cosine 2 pi over 7 plus I sine 2 pi over 7. Let's say Z2 is still 10 times the cosine of 13 pi over 14 plus I sine 13 pi over 14. And this time, let's divide the two. So I need a new R and a new theta, and then I'll put it all together in the polar complex form. So let's find our new R. Remember, our new R is going to be R1 divided by R2. So 5 over 10, let's reduce that. Let's call it 1/2. So that's your new R. let's find your new theta. Is theta 1 minus theta 2? So 2 pi over 7 minus 13 pi over 14. Let's get the common denominator again so we already know what that's going to be. We can call it 4 pi over 14 minus 13 pi over 14. See, guys, when I subtract 4 minus 13, I get negative 9 pi over 14. But remember, if I'm going to put this in polar form, my angle has to be positive. So I have to make this positive. So let's think about it, and we don't do it with radians that much, but when you have a negative angle, this negative theta, whether it's radians or degrees, remember the way to make it positive is to add 360. So I'm going to add 360 to this, and I'm going to get a positive angle. If it's radians, add 2 pi. That's what we're going to use because we're in radians. So I'm going to take my negative 9 pi over 14. I'm going to add a full rotation to it. So I'm going to add 2 pi, and I'll be looking at a coterminal positive angle. You have to make sure you do this because if you try to put a negative angle into a polar form, it's just going to get counted wrong. So you take this, add 2 pi, adding an entire rotation. But of course, because this is a fraction, I have to get common denominators. So I need to take 2 pi over 1 and make it equal something over 14. On the bottom, how did I get from 1 to 14? Well, I multiplied by 14. So I have to multiply by 14 on the top too. So I end up with 28 pi over 14. This is the same thing as 2 pi, but I'm going to use it here so I can add the two fractions together. So my theta is negative 9 pi over 14, and I'm going to add 28 pi over 14 so I can get a positive version of that angle. So negative 9 plus 28, isn't that 21 pi over 14? It is. This is positive, you guys, but if you can reduce, please reduce. You guys, 21 pi over 14 is the same thing as 3 pi over 4. Or, sorry, 2. I don't know why I said 4. You guys, I divided 7 on the top and 7 on the bottom. You get 3 pi over 2. Don't mind me. Okay, so that was a lot of work, yes. But what I got out of it, here's the r I got from dividing the r's. Here's the theta I'm going to use from subtracting the thetas and then getting that angle to be positive. So let's write our quotient, or z1 over z2. That was our goal in this problem. I know it's been a while since we started the problem. But we were looking for z1 over z2. So I got 1/2 because I divided the r's times the cosine of our new angle that I got from subtracting the two thetas. And I get cosine 3 over 2 plus I sine 3 pi over 2. And this is my answer for the division. Okay, so multiply, divide, using the z's. The more you say it, the more you use it, the easier it gets. You won't even have to reference a formula or anything. Just if you're multiplying, multiply the r's, add the thetas. If you're dividing, divide the r's, subtract the thetas. And if you ever run into a situation where you have a negative angle, just get it positive, add a full rotation. Believe me, you guys, I know fractions are not anybody's best friend. Okay. So we can multiply and divide, that's fun. Let's take complex numbers to powers. to Moivre's theorem. So this theorem lets us take a complex number and raise it to a power, which in rectangular form can be really tough, which we'll see in another example. But if you start in polar form, so you have your complex number z, r cosine theta plus I sine theta, and you want to raise the whole thing to a power. So let's say you want z raised to a power, let's call it n. So raise it to any power. Here's what you do. You take r to that power. So you do actually raise r to that power n. But the theta, you don't raise theta to the power. What you do is you multiply theta times that power. So you don't do theta to the n, you just do n times theta to get your new theta. So you guys, de Moivre's theorem is probably the easiest one. You raise r to a power, multiply n times the thetas. So let's look at an example. And notice there's not a z1 and z2 situation here. This is just taking one complex number and raising it to the power n. So I want to do this one where z equals 2 times the cosine of pi over 8 plus I times the sine of pi over 8. This is my z. What I want to find is z raised to the 4th power. So how do I raise everything to the 4th power? Well, I actually do raise r to the 4th power. So it's going to be 2 to the 4th power times the cosine. Remember with the angle, you just multiply by that power. So I'm going to do 4 times pi over 8. So I have 4 times pi over 8 plus I times the sine of 4 times pi over 8. And then let's work this out. So I'm going to put it up here. So z to the 4th, well, 2 to the 4th is 16. So I get 16 times the cosine of 4 pi over 8. So remember, this is 4 over 1. So 4 pi on top, 8 on the bottom, plus I sine 4 pi over 8. But you guys, definitely don't leave it like this. You wouldn't leave it as 4 pi over 8. Let's reduce. So z to the 4th is 16 times the cosine of pi over 2 plus I sine pi over 2. And then this would be your final answer there. Okay, so taking it to powers is pretty easy. I'm not going to do another example of that. But we have multiplied, we've divided, and we've raised things to powers. The last thing we need to do is be able to take roots. Ooh, wait. Hold that thought on the roots. I was going to take another one to a power. I forgot that we have some where you start with rectangular form. So, I'm not a liar. We'll get to roots, I promise. But you guys, you have some that start in rectangular form and it wants you to raise it to a power. So I've got one of those here. So z equals 1 plus I to the 5th. Or z equals 1 plus I. We want to raise this to the 5th power. So what I want is z to the 5th, which would be 1 plus I to the 5th. Notice this is in rectangular form. So you could find the 5th power of this in rectangular form, but you guys, can you imagine how painstaking that would be? You would have to write 1 plus I 5 times and then FOIL it all 5 times. You guys, you would get so many terms and it would just be horrible. So when you're in rectangular form, we hate raising things to powers. That's why de Moivre's theorem is so amazing, because all I gotta do is convert this to polar form and then use the theorem and I'm there, you guys. So, no, this is bad. We do not want to do this. So, here's what I do instead. So on these problems, and you have a couple like this, you need to convert it to polar form first. How do I convert to polar form? Well, I find an r and I find a theta. So, remember this 1 plus I, it's 1 plus 1i. I'm pretty sure we've done this one. But you guys, you're going to get r equals the square root of 1 squared plus 1 squared and get the square root of 2. Your theta, remember that's the inverse tangent of y over x. These are both positive x and y values. It's in the first quadrant where tangent is 1, so our theta is pi over 4. So use your r and theta to write it in polar form. So z in polar form is the square root of 2 times cosine pi over 4 plus I sine pi over 4. Now, that's not answering the question, remember, we're just getting it into polar form, so it's easy to take it to the 5th power. So, let's take it to the 5th power. De Moivre's theorem says that you take r to that 5th power, which we'll do in a second, and then the theta gets multiplied by 5. So you guys, what's pi over 4 times 5? Well, it's 5 pi over 4. So I get cosine 5 pi over 4 plus I sine 5 pi over 4. And you guys, I've taken it to the 5th power. So yes, we have taken it to the power technically. This is the answer for z to the 5th, but I'm pretty sure it wants you to convert it back to standard form on this question. So you converted it to polar. You take it to the power, then you convert it back to rectangular form. So you have that pesky extra step there. But let me show you how easy it is to convert a number back to rectangular form. So remember when we created this, I said there's nothing else you do here. You don't take the sine, you don't take the cosine, you don't do anything. You just leave it in this template. If you want to get it back to rectangular form, all you have to do is work out the math here. So you guys, I have that square root of 2 to the 5th. And then inside here, I'm actually going to, instead of writing cosine 5 pi over 4, I'm going to find the cosine of 5 pi over 4, and I'm going to write it in here, you guys. So here's what the cosine of 5 pi over 4 is. It's negative root 2 over 2. That's in the 3rd quadrant. It's a pi over 4. Plus I times the sine of 5 pi over 4. You guys, that is also negative root 2 over 2. Okay, so we're here. We're really almost done. We need to take care of r. So if you have trouble taking roots to powers, you can always stick it in your calculator. You could write it as, you could write square root of 2 5 times and see what you end up with. You guys, this one, when you have 2 of them, it makes 2, right? When you have 2 of them, it makes 2, and then you have 1 left over. I think that's probably the easiest way to find it. On 2, at least, it's pretty easy. But the square root of 2 to the 5th is going to be 4, and then there's a root 2 left over. So let's write it like that. So instead of writing square root 2 to the 5th, I'm going to write 4 root 2, and then I have times negative root 2 over 2 plus I times negative root 2 over 2. So what I want you to do here is multiply r. Remember, you need to distribute, so multiply it to both terms. So let's write 4 root 2. Let's put it over 1 since we're multiplying it by fractions. So let's distribute it to this term. That's what that looks like. Plus, or actually, before I write a plus there, let's take this minus. Let's go ahead and put it there. Let's call this minus I times 4 root 2 over 1. So r times this last term. And I already took the negative out. So you're just distributing the 4 root 2 to both terms. You guys, what happens with root 2 times root 2? It equals 2, right? So I see a 4 times 2 here with a negative out in front. Well, that's 8. And remember, there's a 2 on the bottom. So I get negative 8 over 2 minus, you guys, what happens here? So I do have an I. 4 root 2 times root 2 again. These 2 root 2's is a 2. So I get a 4 times 2 again. And I get another 8 over 2. So you guys, it ends up simplifying to negative 4 minus 4i. So, yes, it's a lot of work because here's where we started. We had to convert it to polar form, then take it to the 5th power, then actually work out this problem here to get it back to rectangular form. So, nothing you can't do, just kind of a long problem there. Okay, so now it's time for the roots. So you guys, taking the roots of a complex number, it's definitely not anybody's favorite thing to do. And I will hopefully reassure you a little bit. Well, I have to teach it. I have to make sure, you do some homework over it. I'm not going to put it on a test. I'm never going to put it on a test. So with that in mind, all you've got to do is be able to get it through it on your homework. But let's say you have a complex number z, and you want to take, let's say, the nth root. That way we're being general. I want to take the nth root. So when I say nth, I mean maybe the square root or the cubed root, or that number could be the 5th root or the 6th root or whatever. We're calling it the nth root. So I want to find the nth root of z. Remember, z is still our r cosine theta plus I sine theta. And this is how I find it. You guys, you'll notice that anything we want to do to z, we actually do that thing to r. So like when I took it to a power, I actually took r to that power. If I want to take if I want to take z and find the nth root, I find the nth root of r. So there's a couple of ways I can write this. I could write it like this with a little root and then say I want the nth root of r. I'll leave it like that for now. But then let's see what happens to theta. So this is where it gets a little dicey. I am going to have the cosine of theta over n. That makes sense to us. Remember when I took it to a power, I had n times theta. So you would assume if I'm taking a root that it's going to be divided by n. That makes sense, but then there's an extra little part. You have theta over n plus, and you guys, we're going to use degrees on these because we're not that cruel. So plus 360 degrees times a variable k, which I'll help explain in a minute, over n. You guys, this is your angle, which means it also goes in the sine place. So I have I sine theta over n plus 360 degrees times k over n. So n, remember that's the root I want to take. So that's going to be one value. If I say take the 5th root, these n's are all going to be 5s. What is that k? What is happening, right? So you guys, this is where k, so it's actually a sequence. So k, first is going to equal 0. So basically, you're going to put k in here as 0 and get this. Then you're going to put a 1 in there. So k is going to keep getting bigger. So you do all of this with k equals 0, and you get an answer. Then you do all of this with k equals 1, and you get an answer. Then you do all of it with k equals 2, and you do this, and you increase k up until k is n minus 1. So let's explain that. Let's say I want to take the fifth root. These n's are all going to be 5s, and they stay 5s. The first round I do, k will be 0. The second round I do, k will be 1. The third round, k will be 2. Then k will be 3. Then k will be 4. And that's where I stop. K only gets as big as n minus 1. Our n was 5. So k goes up to 4, which means I had to do 0, 1, 2, 3, and 4. So I had to do 5 of these just to get the fifth root. So this is not fun. You guys, there's nothing fun about this, but we can do it. We're going to do an example. So I am going to erase this. Hopefully, if you didn't get that written down, obviously I'm going to be writing it multiple times in a minute, but remember you can always pause and write it down. Okay, so this is finding the nth complex root of a complex number. So you guys, these are going to be given in rectangular form, which means we have to convert it to polar, then do all this mess with the k, and then convert our answers back to rectangular. So it's going to be a little bit tedious. So you guys, I want to find the cube roots, or it says complex roots or something. The cube roots of z equals 4i. So our complex number is 4i. Now, I know we're used to two values being here, an x plus yi, a real and imaginary part. If that throws you, remember you could write this as 0 plus 4i. So like the x is 0 and the y is 4. It's still a complex number, it just has one of the terms is really 0. This is what we're working with. First thing I want to do is put it in polar form. So I need an r. Square root of x squared plus y squared. Remember your x is 0. So I get the square root of 0 squared plus 4 squared. Well, 0 squared is 0. This is the square root of 16, and we get back to that 4. So that should make sense. R is 4. Let's find theta. Theta is the inverse tangent of 4 over 0. All right, so, sorry, I hurt myself up. Okay, so it looks like tangent is undefined for theta. So instead of using our traditional inverse tangent and finding that, why don't we sketch a graph of 4i? It'll be really clear to see where it is. All right, so in your little complex plane, 0 plus 4i. So that means you don't go anywhere on the real axis. You just go up 4. You guys, what angle is this? Well, it's 90 degrees, right? We're looking at a 90-degree angle. That's why tangent broke down here, because the tangent of 90 is undefined. So theta is 90. So this didn't really work out for us, but we found from a picture that theta is 90. Okay, r is 4. Theta is 90. Let's write this in polar form. And try not to lose track of our ultimate goal. So, in rectangular, it was 4i. In polar, it's r, so it's 4 cosine 90 plus I sine 90. You guys, when you're doing problems, this is in degrees. Some of your DeMoss problem are in degrees. be really careful in a calculator, because today or whenever you do this homework, you're going to be back and forth between degrees and radians. So just be careful. But here's where we are. I need to find the nth root, which is the cube roots, is what I'm doing. So I need the cube root of z. Just FYI, we haven't had to use roots as powers like in our whole semester. You might not remember how to write roots as powers, but another way to write, for example, the cube root or the third root is to write z to the 1/3. Another example, if you have the fifth root of something, you could write it as z to the 1/5. So you guys, a fraction power is really just a root. And that's how Alex uses that notation with the fraction powers. So I'm going to try to do that also. So the cube root of z, or z to the 1/3, remember with r, you actually take that root. So I could call it the cube root of 4. I'm going to call it 4 to the 1/3 like Alex does. It might have you write your answer like that, I'm not sure. But I'm going to leave it like that. Then in here, I have the cosine of, let's remember, first it's theta over n. Remember, our n is 3. Let me note that here. N equals 3. So theta is 90. So I have 90 over 3. Remember, that's not all though. Plus 360 degrees times k over 3. I'm going to fill in that k in a minute. Plus I sine, again, theta over 3, plus 360 degrees k over 3. I felt like I sneezed, and then I did. So here we are. You guys, remember k is a moving number. In this line, we start with 0. So in this line, k equals 0. So I put a 0 here and a 0 here, which, you guys, the 0 line is so great because this term just goes away because there's a 0 on the top. So on the 0 line, I get 4 to the 1/3 power times the cosine of 90 degrees over 3. That's all there is there. So that's just the cosine of 30 plus I times the sine of 30. That's not too bad. You guys, we do have to put it back in rectangular form, but we can do that. How do I put it back in rectangular form? So remember, I just actually worked this out, right? What's the cosine of 30? Well, it's root 3 over 2. Plus I times the sine of 30, that's just 1/2. So that's the cubed root of 4. Hold on, cube root of 4. You guys, I don't think, I kind of made this problem up. Let's change that 4 to something that actually has a nice cubed root, because Alex isn't even that cruel to you. So, sorry, I'm not really changing anything except for this 4, and we haven't actually done anything with the 4 yet. But the cube root of 4 is kind of ugly. So, you guys, let's make this an 8. Which means our starting, instead of being 4i, it would have started as 8i. I know that's like a crazy change in the middle of the problem, but let's say we started with 8i, you would have gotten r equals 8 there. So now here we are, and we've got this 8, we're taking the cube root of 8. Oh, but I'm actually going to take it on this line. So you guys, the reason why I didn't use 4 is because 4 isn't a perfect cube. But let's say we were working with 8 the whole time. The cubed root of 8 is 2, so actually call that 2 times root 3 over 2 plus I times 1/2. And what do we get? So you just distribute the 2 to both of these terms, which both have a 2 on the bottom already. So all those 2's cancel out, and you're left with the root 3 plus I. You guys? So you're like, awesome, I got an answer, right? Well, I got a third of an answer. You guys, this is the answer. This is one of the third roots of this 8i when k equals 0. So that's 1/3 of the answer. You put in k equals 0, you get your answer, you put it in rectangular form. But remember, the stupid thing about k is you have to keep changing its value. So now I have to do all of that again for k equals 1. So remember, k steps up. I need to do k equals 1. How does that change? So remember, n is always 3. It's not changing at all, but now I have to put a 1 in here for these two k's. And this is the only place k is, right by the 360. So the cubed root of 8, let's call that 2, times the cosine of what? So we still have the 90 over 3, so you still have the 30, plus 360 times 1, that's 360 over 3, so that's 120. So 30 plus 120, and you just add them together, so you get 150 there. So for the sine, I'm going to go ahead and write 150. So I get 2 times the cosine of 150 plus I sine 150. So you guys, this is your answer in polar form when k equals 1. Put it in rectangular. Remember, you just actually find these values. So I get 2, you guys, the cosine of 150. That's in the second quadrant where cosine is negative. And it's a 30-degree reference, so it's negative root 3 over 2. Plus I times the sine of 150. Sine is positive in the second quadrant, so it's 1/2 again. So work this out. Again, your 2's are canceling, and you get your second and third root, or second cubed root, however you want to say that. You end up with negative root 3 plus I. So similar but different. This is a different root. All right, so actually, let me make a little list. So when k equaled 0, what we got was root 3 plus I. When k equals 1, we just got negative root 3 plus I. Now we have to put in k equals 2. So let's go back to this line here. Remember, all that changes is the k, the number with the 360. This time, we're putting in k equals 2. So everything stays the same except for now there's a 2 here and there's a 2 here. So cubed root of 8, that's 2, times the cosine of, still 90 over 3, so we still get the 30. Plus, you guys, 360 times 2 is 720. And we're going to take that over 3. You guys, what's 720 over 3? I think it's 240. So let's just call it 240. So I did 720 over 3, I got 240. 240 plus 30, that gives us 270. So plus I sine, let's go ahead and call it 270. So you guys, I'm doing the work to find the angle here, and then I'm just copying that angle here. But the work is the same on cosine and sine. So let's simplify that. I get 2 times the cosine of 270 plus I sine 270. So this is the polar form of that third root, the one where k equals 2. Remember to put it in rectangular form, so work it out. What's the cosine of 270? You guys, you have your unit circles. 270 is straight down. Cosine is an x value. The x value, straight down, is 0. So the cosine of 270 is 0, but the sine of 270 is actually -1 because the sine is y and we're straight down. So what's left here? This is really just 2 times 0 minus I, so 2 times -I is all that's left there, and we'll get -2I. This is your last root. Why did I stop at k equals 2? Why didn't I do k equals 3? Because remember, k only goes up to n minus 1, and our n was 3. So it goes 1 less than n every time. And as long as you start with 0 and you go up to that n minus 1 value, you'll notice that if you're looking for the cube roots, you'll get 3 values. We got 3 values. We had to do 3 iterations with k. If we were looking for a 5th root, we would get 5 values because we would use k equals 0, 1, 2, 3, and 4. So if we were doing the 10th root, we would get 10 roots because we'd start with 0 and go up to 9. So keep that in mind. Using the template, remember, the n value doesn't change. It's just each time k gets 1 bigger, 0, 1, 2, 3, and on. Okay, so I know that was a lot. Practice. If you have questions, please get on our Zoom meeting and ask me questions. But this is actually it for your entire week. So you have until, Sunday night to do these 2 sections.